In the boundless tapestry of the cosmos, where light travels for billions of years to reach our eager eyes, there are moments when the universe whispers secrets so profound, so utterly baffling, that they challenge the very foundations of our understanding. Imagine, if you will, a time when the universe was barely an infant, a mere 500 million years old. A time when the first stars were just beginning to ignite, painting the cosmic canvas with nascent light. A time when galaxies, as we know them, should have been scarce, small, and still struggling to form. Yet, what if I told you that in this cosmic dawn, the most powerful eye humanity has ever cast upon the heavens, the James Webb Space Telescope, has peered back through the eons and discovered something truly impossible. Something that defies every expectation, every model, every carefully constructed theory of how our universe came to be. It has found hundreds of galaxies, fully formed, blazing with the light of billions of stars in an era where they simply should not exist. This isn't just a scientific anomaly, it's a cosmic paradox, a profound mystery etched in the blood-red light of the early universe. These are not faint, nascent smudges of gas and dust. These are fully mature, massive galactic behemoths, born in a fraction of the time our current theories allow. They are cosmic impossibilities, celestial rebels that seem to break the fundamental laws of galactic evolution. And their existence forces us to confront a startling question. What if everything we thought we knew about the universe's infancy is wrong? What if the story of creation is far more complex, far more dramatic, and infinitely more bewildering than we ever dared to imagine? Prepare yourselves, fellow cosmic explorers, because today we embark on a journey to the very edge of observable time, to witness a discovery that is rewriting the textbooks of astrophysics. We will delve into the heart of these impossible galaxies, explore the profound implications of their premature birth, and confront the unsettling possibility that our universe is a much stranger, much more dynamic place than we ever conceived. This is a story of scientific triumph, of cosmic wonder, and of a mystery that deepens with every new observation. It's a story that will make you question everything you thought you knew about the cosmos. And if you're as captivated by these cosmic enigmas as I am, if the thought of unraveling the universe's deepest secrets sends a shiver down your spine, then do me a favor. Take a moment right now to hit that like button. It helps us bring more of these incredible cosmic stories to light, and it tells me you're ready to dive deep into the mysteries of the universe with Cosmo Depth. Now let's journey back to a time when the universe was young, and a profound secret was waiting to be unveiled. For decades, our telescopes, even the mighty Hubble Space Telescope, offered us glimpses into the distant universe. But they were like peering through a foggy window. We saw faint, blurry images, hints of what lay beyond, but never the sharp, clear vision needed to truly understand the universe's earliest moments. Then came the James Webb Space Telescope, a marvel of human ingenuity, a technological titan designed to see the universe not in visible light, but in the infrared. Why infrared? Because the universe is expanding, and as light from distant objects travels across billions of light years, its wavelength stretches, shifting from the visible spectrum into the infrared. This phenomenon, known as redshift, is our cosmic clock, telling us not only how far away an object is, but also how long ago its light began its journey. The greater the redshift, the further back in time we are looking, closer to the Big Bang itself. JWST, with its massive 6.5-meter gold-coated mirror and its exquisitely sensitive instruments, was built precisely for this mission: to capture that ancient red-shifted light, to pierce through the cosmic veil and reveal the universe's first stars and galaxies. And it has delivered beyond our wildest dreams. When Webb first turned its gaze to the deepest corners of the cosmos, it didn't just confirm our existing models, it shattered them. It found light from galaxies that existed when the universe was less than 1 billion years old, some even as young as 300 million years post-Big Bang. These were not the small, irregular, barely there proto-galaxies we expected. No, what Webb found were fully formed, luminous galaxies brimming with stars, some as massive as our own Milky Way, but existing at a time when they simply shouldn't have had enough time to grow so large. Imagine a newborn baby, just a few months old, not only walking, but running a marathon. That's the scale of the cosmic anomaly we're talking about. The universe, according to our prevailing cosmological models, needed time for gravity to slowly pull together gas and dust, for stars to form, explode, and enrich the interstellar medium, and for these processes to gradually build up structures as complex as galaxies. Yet, here they are, these ancient giants, staring back at us from the cosmic infancy, challenging everything we thought we knew. They are the universe's early bloomers, the cosmic overachievers, and their existence demands an explanation that our current theories struggle to provide. This isn't just a minor adjustment to our understanding. It's a potential paradigm shift, a rewriting of the cosmic narrative. And as we continue to explore these impossible galaxies, we are forced to confront the limits of our knowledge and the boundless mysteries that still await us in the vast expanse of space. To truly grasp the magnitude of this discovery, we need to understand the cosmic framework against which it is measured, the lambda c.d. M model. This is our standard model of cosmology, the prevailing scientific consensus that describes the universe from its very beginning, the Big Bang, to its current state. Lambda CDM stands for lambda, LAMBDA, representing dark energy and cold dark matter, CDM. It posits that our universe is made up of about 5% ordinary matter, the stuff we can see and touch, 27% dark matter, an invisible substance that interacts gravitationally but not electromagnetically, and 68% dark energy, a mysterious force driving the accelerated expansion of the universe. This model has been incredibly successful, explaining a vast array of cosmological observations, from the cosmic microwave background radiation to the large-scale structure of the universe. According to Lambda CDM, the early universe was a much simpler place. After the Big Bang, the universe was a hot, dense plasma that gradually cooled and expanded. Gravity, acting on tiny fluctuations in this primordial soup, began to pull together concentrations of dark matter, forming invisible halos. These dark matter halos acted as gravitational wells, slowly attracting ordinary gas, which then cooled and collapsed to form the first stars. These first stars, massive and short-lived, forged heavier elements and eventually exploded as supernovae, scattering these elements into space. Over vast stretches of cosmic time, these processes repeated, leading to the gradual assembly of larger and larger structures, the first small galaxies, which then merged and accreted more matter to grow into the majestic spirals and ellipticals we see today. The key word here is gradual. The lambda CDM model predicts a hierarchical formation of galaxies, meaning small galaxies form first and then merge and grow over billions of years. Therefore, when we look back to the early universe, say 500 million to a billion years after the Big Bang, we expect to see only nascent, relatively small and irregular proto-galaxies, still in the very early stages of their development. We certainly don't expect to find fully formed, massive galaxies, teeming with billions of stars, as luminous and mature as those that took billions of years to form in the later universe. Yet, this is precisely what James Webb Space Telescope has found. These 300 galaxies, observed at redshifts corresponding to a time when the universe was less than 1 billion years old, are not the faint, struggling infants our models predicted. They are cosmic titans, already boasting stellar masses comparable to the Milky Way, our own galaxy, which took over 13 billion years to reach its current size. This is like finding a fully grown adult in a kindergarten classroom. The sheer speed at which these galaxies must have assembled their stars and mass is simply astounding, and it presents a significant challenge to the lambda CDM model. It's not that the model is entirely wrong. It's more like it's incomplete, or perhaps our understanding of the parameters within it needs a radical re-evaluation. The universe, it seems, had a few surprises up its sleeve, and JWST is pulling back the curtain on a cosmic drama far more complex and accelerated than we ever imagined. The James Webb Space Telescope is not just a telescope, it's a time machine, capable of peering back to within a few 100 million years of the Big Bang. Its primary instruments, the near-infrared camera, NIRCAM, and the mid-infrared instrument, MIRI, are designed to detect the faint, stretched-out light from these ancient cosmic objects. Imagine trying to see a candle flame from across a continent. That's the challenge astronomers face, but Webb makes it possible. When the Mizu research team, led by Professor Haojing Yan and PhD student Bangjeng Tom Sun, analyzed the infrared images captured by Webb, they weren't just looking for bright spots, they were looking for specific signatures in the light that would betray the age and distance of these galaxies. The key to unlocking the universe's past lies in a phenomenon called redshift. As the universe expands, it stretches the very fabric of space-time. Light waves traveling through this expanding space also get stretched, shifting towards the red end of the electromagnetic spectrum. The more distant an object, the more its light is redshifted, and the further back in time we are observing it. So, a galaxy with a redshift of, say, 10 means its light has traveled for over 13 billion years to reach us, originating from a time when the universe was less than 500 million years old. Webb's instruments are perfectly tuned to capture these highly redshifted signals, allowing us to see galaxies that were previously invisible to even the most powerful telescopes. To identify these elusive early galaxies, the researchers employed a clever technique known as the dropout method. This method relies on a specific spectral feature called the Lyman break. In essence, neutral hydrogen gas in the early universe absorbs ultraviolet light from young, hot stars in galaxies. As a galaxy's light travels through space and gets redshifted, this absorption feature, the Lyman break, shifts into the infrared part of the spectrum. By looking for objects that appear in redder infrared wavelengths but drop out or vanish in bluer infrared wavelengths, astronomers can pinpoint high redshift galaxies. It's like a cosmic filter, allowing only the light from the most ancient galaxies to pass through in certain colors. Once these candidate galaxies are identified, the next step is to estimate their properties, their distance, age, and mass. While the gold standard for this is spectroscopy, which spreads light into its constituent wavelengths to reveal a galaxy's unique chemical fingerprint, it's not always immediately available for every object. For these 300 mysterious objects, the team used a technique called spectral energy distribution fitting. This involves comparing the observed brightness of a galaxy across different infrared wavelengths to theoretical models of galaxy light. By finding the best fit, they can estimate the galaxy's redshift, stellar mass, and even its star formation rate. And what these estimations revealed was nothing short of astonishing. These weren't just any early galaxies. They were massive early galaxies. Galaxies that had already accumulated billions of stars, formed complex structures, and were shining with an intensity that defied the slow, gradual build-up predicted by our standard cosmological models. The sheer number of them, 300 such objects in the small patches of sky observed by Webb, further amplified the mystery. It wasn't an isolated anomaly. It was a widespread phenomenon. The universe, it seemed, was forming galaxies much faster and much more efficiently in its infancy than anyone had ever anticipated. This wasn't just a minor tweak to our understanding. It was a fundamental challenge, a cosmic riddle demanding a new solution. The discovery of these unexpectedly massive and mature galaxies in the early universe has sent ripples through the astrophysical community. These objects, sometimes colloquially referred to as red monsters due to their redshifted light and immense stellar populations, present a profound challenge to our understanding of galaxy formation and evolution. The core of the problem lies in the timescale. According to the lambda CDM model, the universe was simply too young for galaxies to have accumulated so much mass and formed so many stars. Think of it this way. The universe is approximately 13.8 billion years old. If we are observing galaxies that existed when the universe was, say, 500 million years old, that means they had only a tiny fraction of cosmic history to develop. For a galaxy to reach a mass comparable to the Milky Way in such a short period, it would require an incredibly efficient and rapid process of star formation. Our current models suggest that star formation in the early universe should have been a much slower, more arduous affair, limited by the availability of cold gas, the efficiency of gravitational collapse, and the disruptive feedback from supernovae and early black holes. One of the primary constraints is the growth of dark matter halos. Dark matter is the scaffolding upon which galaxies are built. In the early universe, these halos were smaller and less numerous. For a galaxy to become massive, it needs to reside within a sufficiently massive dark matter halo. The problem is that the lambda CDM model predicts that such massive halos simply hadn't had enough time to form and grow to the sizes required to host these red monsters in the early epochs observed by JWST. It's a fundamental mismatch between the observed stellar mass of these galaxies and the predicted mass of their host dark matter halos. Furthermore, the process of star formation itself is not instantaneous. Gas needs to cool, condense, and overcome various turbulent forces to form stars. While the early universe had abundant hydrogen and helium, the raw ingredients for stars, the mechanisms for rapidly converting vast quantities of this gas into stars remain a puzzle. If these galaxies were indeed forming stars at an unprecedented rate, where did all that gas come from? And what powered such a frenzied burst of stellar creation? Another aspect of the problem is the chemical enrichment of these galaxies. When stars form and die, they produce heavier elements, everything beyond hydrogen and helium. These elements are then recycled into the interstellar medium, contributing to subsequent generations of stars. The presence of mature stellar populations in these early galaxies implies that several generations of stars must have already lived and died, enriching their environments with heavy elements. This process also takes time, and the sheer amount of chemical enrichment observed in some of these early galaxies seems inconsistent with their tender cosmic age. So, these red monsters are not just an interesting curiosity. They are a direct challenge to the timeline of cosmic evolution as we currently understand it. They force us to ask, is there a missing piece in our understanding of gravity, dark matter, or the very process of star formation? Or are these observations hinting at something even more revolutionary? Something that could fundamentally alter our cosmological paradigm? The universe, it seems, is far more precocious than we ever gave it credit for. The existence of these cosmic leviathans in the universe's infancy demands an explanation, and astrophysicists are now scrambling to find answers, proposing several intriguing possibilities that could reconcile these observations with our broader cosmological framework. Each potential solution forces us to re-examine fundamental assumptions about the universe's earliest moments. One leading hypothesis suggests that star formation in the early universe was far more efficient than previously imagined. Our current models often assume a relatively steady rate of star birth. But what if the conditions in these nascent galaxies were perfect for a rapid, explosive burst of stellar creation? Imagine vast reservoirs of pristine hydrogen and helium gas, unpolluted by heavier elements, collapsing under gravity without the disruptive feedback from supernovae or active galactic nuclei that can suppress star formation in later epochs. This scenario, sometimes referred to as bursty star formation, could allow galaxies to accumulate stellar mass at an astonishing rate, essentially cramming billions of years of star-forming activity into a much shorter cosmic timeframe. Perhaps the early universe was a much more violent and dynamic place, with intense gravitational instabilities driving gas directly into star-forming regions, leading to a quick and brutal assembly of stellar populations. Another avenue of investigation focuses on the properties of dark matter and the initial conditions of the universe. The lambda CDM model assumes a specific distribution of dark matter halos, which act as the gravitational scaffolding for galaxies. If, however, the initial density fluctuations in the very early universe were slightly larger or distributed differently than our models predict, it could have led to the formation of more massive dark matter halos much earlier. These larger halos would then have provided deeper gravitational wells capable of attracting and holding more gas, thereby accelerating the galaxy formation process. This wouldn't necessarily mean a complete overhaul of lambda CDM, but rather a refinement of its parameters or a deeper understanding of the processes that seeded the universe with its initial structure. A more radical proposal involves modifications to our understanding of dark matter itself. While cold dark matter has been incredibly successful in explaining many cosmic phenomena, some researchers are exploring alternative dark matter candidates or interactions. Could dark matter have properties that allowed it to clump together more rapidly in the early universe, thereby accelerating the formation of galactic structures? Or perhaps there are subtle interactions between dark matter and ordinary matter that we haven't yet accounted for, which could influence the efficiency of gas accretion and star formation. These are speculative ideas, pushing the boundaries of our current physics, but the profound nature of JWST's discoveries warrants such bold thinking. Furthermore, there's always the possibility that our interpretation of the observational data needs refinement. While JWST is an unparalleled instrument, interpreting the faint, red-shifted light from billions of light years away is an incredibly complex task. Are we accurately measuring the stellar masses of these galaxies? Are there biases in our observations that make them appear brighter or more massive than they truly are? For instance, some of these objects might be hosting exceptionally bright, active galactic nuclei, AGN, supermassive black holes at their centers that are actively accreting matter and emitting vast amounts of radiation. If these AGNs are particularly luminous, they could be artificially inflating our estimates of the host galaxy's stellar mass. While this doesn't fully explain the existence of so many massive galaxies, it could account for some of the extreme outliers. Another consideration is the initial mass function of stars in the early universe. The IMF describes the distribution of stellar masses at birth. If the early universe favored the formation of more massive stars, these stars would burn brighter and die faster, enriching the galaxy with heavy elements more quickly. However, this would also mean a faster depletion of gas and a shorter period of intense star formation, which might not fully explain the sustained mass buildup observed. Ultimately, these early galaxies are forcing us to confront the limits of our current models. They are cosmic laboratories, providing us with unprecedented data from a critical epoch in the universe's history. The answers may lie in a combination of these factors, or perhaps in an entirely new physical process we haven't even conceived of yet. What is clear is that JWST is not just observing the universe. It's actively participating in the rewriting of its origin story, pushing us to think beyond our current paradigms and embrace the universe's inherent capacity for surprise. These newly discovered galaxies are not just massive. They possess other characteristics that further deepen the mystery and challenge our conventional understanding. When astronomers analyze the light from these distant objects, they can infer details about their stellar populations, their chemical composition, and even their morphology. And what they're finding is a universe far more complex and evolved in its infancy than previously believed. Many of these early galaxies appear to be rich in dust and heavy elements, which is another significant puzzle. Heavy elements, or metals in astronomical parlance, are forged in the hearts of stars and dispersed into space through supernova explosions. For a galaxy to be chemically enriched, multiple generations of massive stars must have already lived and died. This process takes time. Yet, these early galaxies, some observed just a few 100 million years after the Big Bang, already show signs of significant metal enrichment, implying a rapid and efficient cycle of star birth and death that is difficult to reconcile with their young age. It's like finding an ancient artifact that appears brand new, defying the natural wear and tear of time. Furthermore, some of these galaxies exhibit surprisingly well-defined structures, with hints of disks and spiral arms, or at least a more organized morphology than the chaotic, clumpy proto-galaxies our models predicted for that era. Early galaxies were expected to be irregular, undergoing frequent mergers and lacking the gravitational stability to form coherent structures. The presence of even nascent ordered structures suggests a level of dynamical maturity that is truly astonishing for such a young universe. It implies that the processes leading to galactic organization were far more accelerated or efficient than previously thought. These galaxies also play a critical role in understanding a pivotal period in cosmic history known as the Epoch of Rhionization. After the Big Bang, the universe was a hot, dense plasma. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, rendering the universe dark and opaque to ultraviolet light. This period is often called the Cosmic Dark Ages. Then, a few 100 million years after the Big Bang, something began to raionize this neutral hydrogen, transforming the universe back into a transparent, ionized state. This cosmic dawn is believed to have been driven by the first stars and galaxies, which emitted powerful ultraviolet radiation that stripped electrons from hydrogen atoms. The problem is, our previous models struggled to identify enough sources of ionizing radiation to fully account for the observed reionization of the universe. The discovery of these hundreds of unexpectedly bright and massive galaxies by JWST offers a potential solution. If these galaxies were indeed forming stars at an incredibly rapid pace, they would have been prodigious emitters of ultraviolet light, capable of producing the necessary photons to raionize the universe. Their sheer number and luminosity could provide the missing puzzle piece in our understanding of how the universe transitioned from its dark ages to the transparent, star-filled cosmos we see today. They are not just anomalies. They might be the very engines that lit up the early universe, paving the way for everything that came after. Their existence forces us to reconsider the entire timeline of cosmic events, placing these impossible galaxies at the heart of the universe's grand awakening. The revelations from the James Webb Space Telescope are not just rewriting chapters in our cosmic history books. They are opening entirely new volumes, posing profound questions that will drive astrophysical research for decades to come. The existence of these 300 galaxies that shouldn't exist forces us to confront the limits of our current understanding and embark on a new era of cosmic exploration, both observational and theoretical. One of the most immediate and crucial next steps is to obtain spectroscopic confirmation for a larger sample of these candidate galaxies. As we discussed, while the dropout method and spectral energy distribution fitting provide strong evidence, spectroscopy is the gold standard for precisely determining redshift, stellar mass, and chemical composition. Webb's near-infrared spectrograph and mid-infrared instrument, MIRI, are perfectly suited for this task. By obtaining detailed spectra of these galaxies, astronomers can confirm their distances with absolute certainty, measure their star formation rates, and analyze their chemical fingerprints with unprecedented accuracy. This will allow us to move beyond statistical estimations and confront the models with hard, undeniable data. If a significant number of these galaxies are spectroscopically confirmed to be as massive and mature as they appear, the challenge to existing cosmological models will become even more undeniable. Beyond confirmation, future research will focus on understanding the physical mechanisms that allowed these galaxies to grow so rapidly. This involves refining our simulations of galaxy formation to incorporate new physics or to explore extreme conditions that might have existed in the early universe. Could there have been more efficient cooling mechanisms for gas? Were the initial density fluctuations in the early universe larger than previously assumed, leading to more massive dark matter halos forming earlier? Or perhaps the early universe was teeming with a different kind of dark matter, one that clustered more aggressively. Another critical area of investigation will be the role of supermassive black holes, SMBHs, in these early galaxies. We know that most massive galaxies today host a supermassive black hole at their center, and there's a strong correlation between the mass of the black hole and the mass of its host galaxy's bulge. Did these early massive galaxies also host rapidly growing SMBHs? If so, did these black holes contribute to the rapid star formation through feedback mechanisms? Or did they grow in tandem with their host galaxies in an accelerated fashion? Webb's observations are already hinting at the presence of active galactic nuclei in some of these early systems, suggesting a complex interplay between black hole growth and galaxy evolution, even in the universe's infancy. The implications extend beyond just galaxy formation. These discoveries could also shed new light on the nature of dark matter and dark energy. If the lambda CDM model struggles to explain these observations, it might indicate that our understanding of these fundamental components of the universe is incomplete. Perhaps dark matter has properties that allow it to clump more readily in the early universe. Or dark energy's influence was different in the very early epochs. While these are highly speculative, the scientific process demands that we consider all possibilities when confronted with such profound anomalies. Finally, these findings will undoubtedly lead to a re-evaluation of the cosmic dawn and the epoch of Ryanization. If these early galaxies were indeed more numerous and luminous than anticipated, they could have been the primary drivers of Ryanization, providing the necessary ultraviolet photons to ionize the neutral hydrogen that pervaded the early universe. Understanding the properties and distribution of these galaxies will be crucial for building a complete picture of how the universe transitioned from its dark ages to the transparent star-filled cosmos we inhabit today. The James Webb Space Telescope is not just a window to the past. It's a catalyst for a future where our cosmic narrative is richer, more complex, and infinitely more awe-inspiring than we ever dared to dream. The universe, it seems, is always ready to surprise us, and with every new discovery, we are drawn deeper into its profound and beautiful mysteries. The lambda CDM model, for all its successes, operates on a fundamental timeline for cosmic structure formation. It's a carefully constructed narrative of gravitational assembly, where smaller structures coalesce to form larger ones over vast stretches of cosmic time. This hierarchical formation is a cornerstone of the model, predicting a universe where the earliest galaxies are necessarily small, nascent, and relatively inefficient at star formation. The discovery of these hundreds of massive luminous galaxies in the early universe directly contradicts this predicted timeline, creating a profound tension that demands resolution. Consider the cosmic dark ages, the period after the universe cooled enough for neutral hydrogen to form, but before the first stars and galaxies reionized the intergalactic medium. During this era, gravity was the primary architect, slowly drawing together the invisible scaffolding of dark matter. These dark matter halos, as they grew, would then attract ordinary baryonic matter, gas, and dust, which would eventually cool and collapse to form stars. The rate at which these halos could grow and accumulate mass is constrained by the expansion of the universe and the properties of dark matter itself. Our simulations, based on lambda CDM, consistently show that truly massive dark matter halos, capable of hosting galaxies like the Milky Way, should not have been abundant enough or large enough to form so early in the universe's history. Yet, JWST is showing us that such massive galaxies were not just rare anomalies, but seemingly commonplace. This isn't merely a quantitative discrepancy, it's a qualitative one. It's not just that these galaxies are a bit bigger than expected. They are fundamentally different from what the models predicted. They are already mature, with significant stellar populations, and in some cases, evidence of chemical enrichment that implies a rapid succession of star formation and supernova events. This maturity, observed so early, suggests an accelerated pace of cosmic evolution that the lambda CDM framework struggles to accommodate. It implies that the initial conditions of the universe, or the processes governing star and galaxy formation, were far more potent and efficient than previously assumed. Imagine trying to build a skyscraper in a matter of days when the blueprints and construction methods dictate months or years. That's the kind of challenge these early galaxies present. They seem to have bypassed several crucial steps in the cosmic construction process, or perhaps they utilized an entirely different, faster method. This forces cosmologists to re-examine the very parameters of the lambda CDM model. Could the universe have been slightly denser in its early stages? Could dark matter have interacted in ways we don't yet understand, facilitating faster collapse? Or could the efficiency of converting gas into stars have been orders of magnitude higher than our current estimates? The implications are far-reaching. If the early universe was capable of forming such massive structures so quickly, it could mean that the seeds of cosmic structure were laid down with greater initial variations than previously thought. It could also mean that the processes of gas cooling and accretion onto dark matter halos were far more efficient, allowing for a rapid influx of material to fuel intense bursts of star formation. These galaxies are not just pushing the boundaries of our telescopes, they are pushing the boundaries of our theoretical understanding, forcing us to confront the possibility that the universe's earliest chapters are far more dramatic and surprising than we ever conceived. When we call these galaxies cosmic impossibilities, it's not hyperbole. It's a direct reflection of the profound dissonance between observation and theory. Imagine peering through a telescope, expecting to see faint, wispy clouds of gas, perhaps with a few struggling stars, and instead finding a bustling metropolis, fully illuminated, with towering structures and a vibrant population. That's the scale of the surprise JWST has delivered. These aren't just slightly larger than expected. They are galactic titans, already possessing the mass and maturity that should have taken billions of years to acquire. Let's break down what makes them so impossible. Firstly, their stellar mass. Many of these early galaxies have stellar masses comparable to, or even exceeding, that of our own Milky Way galaxy. The Milky Way, a majestic spiral, has had over 13 billion years to accumulate its stars, to undergo countless mergers, and to slowly build up its impressive bulk. For a galaxy to achieve a similar stellar mass in less than a billion years, some even as early as 300 to 500 million years after the Big Bang, implies a star formation, efficiency that is almost unimaginable. It's like a human infant reaching adult size and cognitive ability within a few months of birth. The sheer rate at which these galaxies must have converted their gas into stars is a staggering challenge to our models of star formation. Secondly, their luminosity. These galaxies are incredibly bright, shining with the light of billions upon billions of stars. This extreme luminosity is a direct consequence of their immense stellar populations and likely a high rate of ongoing star formation. But this brightness also means they are burning through their stellar fuel at an astonishing pace. If they formed so many stars so quickly, what does that imply for their longevity? Were they destined to be short-lived, brilliant beacons that faded quickly? Or did they find a way to sustain this frenetic activity over longer timescales? Thirdly, the chemical enrichment. As we touched upon, stars are the universe's alchemists, forging heavier elements from primordial hydrogen and helium. When massive stars die in supernova explosions, they scatter these newly forged elements into the surrounding gas, enriching the galaxy. Subsequent generations of stars then form from this enriched material. The presence of significant amounts of heavy elements in these early galaxies implies that not only did they form stars rapidly, but these stars also lived, died, and recycled their material back into the galaxy at an accelerated rate. This rapid chemical evolution is another piece of the puzzle that doesn't fit the traditional timeline. It suggests a cosmic assembly line operating at warp speed, churning out stars and elements far faster than our models predict. Fourthly, their morphology and structure. While detailed structural analysis is still ongoing, preliminary observations suggest that some of these early galaxies are not the chaotic, clumpy blobs we expected. Instead, they show hints of more organized structures, even nascent disks. The formation of stable, rotating disks requires a period of gravitational settling and dynamic evolution, processes that typically take billions of years. To see even the beginnings of such organization in galaxies so young is another head-scratching observation. It implies that the gravitational forces and internal dynamics within these nascent galaxies were somehow accelerated, allowing them to settle into more mature configurations much faster than our models allow. These combined properties paint a picture of a universe that was far more precocious and efficient at building galaxies than we ever imagined. It's as if the universe, in its infancy, was already in a hurry, skipping developmental stages and leaping straight to galactic maturity. This isn't just a minor adjustment to our cosmic ledger. It's a fundamental challenge to the very narrative of cosmic evolution, forcing us to reevaluate the physics that governed the universe's earliest and most formative years. The implications are profound, potentially pointing towards new physics, revised cosmological parameters, or a completely different understanding of how the cosmos orchestrated its grand symphony of creation. To appreciate the sheer ingenuity behind these discoveries, it's crucial to understand the sophisticated observational techniques employed by the James Webb Space Telescope. This isn't just about pointing a powerful lens at the sky. It's about meticulously collecting and interpreting faint signals that have traveled across nearly the entire age of the universe. The success of JWST in uncovering these impossible galaxies lies in its unparalleled sensitivity, its infrared capabilities, and the clever strategies astronomers use to sift through the cosmic noise. Webb's primary instruments, NIR-CAM, near-infrared camera, and MIRI, mid-infrared instrument, are the workhorses of its deep-field observations. NIR-CAM, with its broad wavelength coverage from 0.6 to 5 microns, is adept at capturing the light from highly redshifted objects. MIRI extends this capability into the mid-infrared, from 5 to 28 microns, allowing it to peer through dust and detect cooler, more evolved stellar populations. These instruments are equipped with an array of filters, each designed to capture light within a very specific wavelength range. By observing a patch of sky through multiple filters, astronomers can build up a spectral energy distribution SED for each detected object, essentially a graph showing how bright an object is at different wavelengths. This multi-filter approach is fundamental to the dropout technique we discussed earlier. Imagine a series of cosmic sieves, each with a different mesh size. Light from a very distant galaxy, having been significantly redshifted, might pass through the redder filters but be completely blocked by the bluer ones due to the Lyman alpha absorption feature. When an object drops out of the bluer filters but appears clearly in the redder ones, it's a strong indicator that it's a high redshift galaxy located deep in the early universe. This method has been refined over years with telescopes like Hubble, but JWST's superior sensitivity and infrared reach have pushed its effectiveness to unprecedented cosmic distances. But identifying these candidates is just the first step. The next, and arguably more challenging phase, is to confirm their distances and characterize their properties. This is where spectroscopy comes into play. Webb's NIR-SPEC, near-infrared spectrograph, and MIRI's MRS, medium-resolution spectrometer, are designed to spread the light from these faint galaxies into a rainbow of individual wavelengths. Each element in the universe absorbs and emits light at characteristic wavelengths, creating a unique fingerprint in the spectrum. By identifying these spectral lines, astronomers can precisely measure the redshift of a galaxy, thereby determining its exact distance and the cosmic epoch from which its light originated. Furthermore, the strength and shape of these spectral lines reveal crucial information about the galaxy's chemical composition, its star formation rate, the presence of active galactic nuclei, and even the motion of gas within it for many of the 300 galaxies in question. Initial observations relied on photometric redshifts, estimates derived from their brightness across different filters. While these are good first approximations, they carry inherent uncertainties. The ongoing and future spectroscopic campaigns with JWST are critical to solidify these findings. When a photometric redshift is confirmed by a spectroscopic redshift, it moves from a candidate to a confirmed early galaxy. And each confirmation strengthens the case that these impossible galaxies are indeed real, challenging our models in a tangible, undeniable way. The sheer number of these discoveries is also a testament to Webb's capabilities. In relatively small patches of the sky, JWST has revealed a universe teeming with these early, massive structures. This suggests that their existence is not an isolated phenomenon or a statistical fluke, but rather a widespread characteristic of the universe's infancy. The cosmic landscape of the early universe, as painted by Webb, is far more vibrant, complex, and populated than we ever dared to imagine, forcing us to re-evaluate the very canvas upon which the story of cosmic evolution is unfolding. The data is in, and it's telling a story that is both exhilarating and deeply perplexing. One might wonder if these discoveries are simply statistical flukes, isolated anomalies in the vastness of space. Perhaps we just happen to look at a particularly dense region of the early universe, a cosmic aberration that doesn't represent the norm. This concept is known as cosmic variance, the idea that different regions of the universe, especially on smaller scales, can have different properties due to random fluctuations in the early universe. However, the sheer number and consistency of these observations across various JWST deep fields are rapidly diminishing the likelihood that cosmic variance alone can explain this phenomenon. Astronomers have observed these unexpectedly massive and mature galaxies in multiple independent fields across the sky. This widespread detection suggests that their existence is not a localized quirk, but a fundamental feature of the early universe. If it were just one or two such galaxies, we might dismiss them as outliers or observational errors. But when hundreds of them appear, consistently defying our expectations, it points to a systemic issue with our current models rather than a statistical anomaly. The universe, it seems, was simply more efficient at building galaxies in its youth than our theories had predicted. This statistical significance is what truly elevates these findings from interesting curiosities to profound challenges. It means that the conditions necessary for rapid galaxy formation were not rare or exceptional. They were, in fact, quite common across the early cosmos. This forces us to re-evaluate the average conditions of the universe during its infancy, suggesting a more dynamic and accelerated evolutionary pathway for cosmic structures than previously considered. The implications of this widespread galactic precocity are far-reaching. If our standard lambda CDM model cannot adequately explain the abundance and maturity of these early galaxies, it suggests that there might be new physics at play, or at least a significant refinement needed in our understanding of existing physics. This could manifest in several ways. Firstly, it could point to a more complex nature of dark matter. While cold dark matter has been incredibly successful, perhaps there are subtle interactions or properties of dark matter that allow it to clump more efficiently in the early universe, leading to the formation of more massive dark matter halos at earlier times. Theories involving warm dark matter or self-interacting dark matter, while not currently favoured, might gain new traction if they can better explain these observations. Secondly, it might require a re-evaluation of the initial conditions of the universe. The lambda CDM model relies on a specific spectrum of primordial density fluctuations, tiny ripples in the early universe that seeded all subsequent structure. If these fluctuations were slightly larger on certain scales, or had a different statistical distribution, it could have accelerated the formation of massive structures. This would require going back to the very first moments after the Big Bang, perhaps even probing the physics of cosmic inflation, the hypothesized period of exponential expansion that smoothed out the universe and generated these initial fluctuations. Thirdly, and perhaps most excitingly, these observations could hint at entirely new astrophysical processes that were dominant in the early universe, but have since become less significant. Could there have been exotic forms of early star formation, perhaps involving direct collapse of massive gas clouds into supermassive stars or even intermediate mass black holes, which then rapidly seeded galaxy growth? Or perhaps the interaction between early galaxies and the intergalactic medium was far more efficient at funneling gas into star-forming regions. The beauty of science lies in its ability to adapt and evolve in the face of new evidence. These impossible galaxies are not a sign of failure, but a beacon guiding us towards a deeper, more accurate understanding of the cosmos. They are forcing us to push the boundaries of our theoretical frameworks, to consider possibilities we once deemed too exotic, and to embark on a journey into uncharted scientific territory. The universe, through the eyes of JWST, is revealing itself to be a place of constant surprise, where the most fundamental truths are always open to re-examination. One of the most profound implications of these early, massive galaxies directly relates to a pivotal, yet still largely mysterious, chapter in cosmic history, the epoch of reionization. To understand this, we need to rewind to the universe's earliest moments. After the Big Bang, the universe was a scorching hot, dense soup of fundamental particles. As it expanded and cooled, about 380,000 years after the Big Bang, electrons and protons combined to form neutral hydrogen atoms. This event made the universe transparent to light for the first time, allowing the cosmic microwave background radiation to stream freely. However, the universe then entered a period often referred to as the cosmic dark ages. There were no stars, no galaxies, just a vast dark expanse of neutral hydrogen gas. This darkness persisted for several 100 million years until the first stars and galaxies began to ignite. These pioneering luminous objects emitted intense ultraviolet UV radiation. UV light has enough energy to strip electrons from neutral hydrogen atoms, a process called ionization. As more and more stars and galaxies formed, they gradually created bubbles of ionized hydrogen that expanded and eventually merged, transforming the entire universe from an opaque, neutral state back into the transparent, ionized state we observe today. This grand cosmic transformation, spanning from roughly 150 million to about 1 billion years after the Big Bang, is the epoch of reionization. For decades, astronomers have struggled to identify enough sources of ionizing photons to account for the complete reionization of the universe. Our previous models, based on observations from telescopes like Hubble, suggested that the early galaxies were too small and too few to produce the sheer quantity of UV radiation needed. It was a cosmic energy crisis. Where did all the light come from to reionize the universe? Some theories proposed exotic sources, like decaying dark matter or mini-quasars, but the primary candidates have always been the first generations of stars within the first galaxies. The discovery of hundreds of unexpectedly bright and massive galaxies by JWST offers a compelling and potentially complete solution to this cosmic energy crisis. If these galaxies were indeed forming stars at an incredibly rapid and efficient pace, they would have been prodigious factories of UV light. Their sheer number and luminosity mean that the early universe was far more ablaze with star formation than previously thought. These impossible galaxies, far from being mere anomalies, might have been the very cosmic furnaces that burned away the primordial fog, illuminating the universe and making it transparent for the first time since the Big Bang. Imagine the universe as a vast, dark ocean, and these galaxies as powerful lighthouses, slowly but surely cutting through the gloom. The more lighthouses and the brighter they shine, the faster the ocean becomes navigable. JWST's findings suggest that the early universe was not just dotted with a few dim lanterns, but was teeming with brilliant beacons, rapidly pushing back the darkness. However, even with this potential solution, mysteries remain. The exact timeline and morphology of reionization are still debated. Did reionization happen uniformly across the universe, or in a patchy, bubble-like fashion? What was the relative contribution of different types of galaxies? And what role did active galactic nuclei, powered by supermassive black holes, play in this process? While these massive early galaxies provide a strong candidate for the primary drivers of reionization, detailed spectroscopic observations are still needed to precisely quantify their output of ionizing photons and to map out the reionization process with unprecedented clarity. JWST continues to be our most powerful tool in unraveling this complex and transformative period, allowing us to witness almost firsthand the universe's grand awakening from its long, dark slumber. As if the rapid formation of massive galaxies wasn't enough of a cosmic enigma, these early observations by JWST are also forcing us to reevaluate the origins and growth of another fundamental component of the universe: supermassive black holes, SMBHS. We know that nearly every massive galaxy in the local universe harbors an SMBH at its center, with masses ranging from millions to billions of times that of our Sun. There's a well-established correlation between the mass of the central black hole and the stellar mass of its host galaxy's bulge, suggesting a profound co-evolutionary relationship. But how did these monstrous black holes form so early in the universe? And how did they grow so rapidly in tandem with their host galaxies? According to traditional models, SMBHS are thought to grow primarily through two mechanisms: accreting gas and dust from their surroundings and merging with other black holes. Both processes take time. The seeds of these SMBHs are believed to be either the remnants of the first massive stars, stellar mass black holes, or direct collapse black holes formed from the collapse of massive gas clouds in the early universe. However, growing these initial seeds into billion solar mass behemoths within a few 100 million years after the Big Bang presents a significant challenge. JWST's observations are revealing that many of these early massive galaxies are not just forming stars at an astonishing rate, but some also appear to host actively accreting supermassive black holes, often referred to as active galactic nuclei AGN or quasars. These AGNs are incredibly luminous, outshining their entire host galaxies as matter spirals into the black hole, heating up and emitting vast amounts of radiation across the electromagnetic spectrum. The presence of such powerful AGNs in the early universe implies that their central black holes were already incredibly massive and actively feeding at a time when they should have still been relatively small and nascent. This rapid growth of both galaxies and their central black holes presents a dual conundrum. How did the black holes accumulate so much mass so quickly? And what was the nature of their interaction with their host galaxies? Did the black holes grow first, providing feedback that either triggered or quenched star formation? Or did the rapid star formation in the host galaxy provide ample fuel for the black hole to grow? One hypothesis suggests that the early universe might have provided more favorable conditions for direct collapse. Black holes DCBHS. Instead of forming from stellar remnants, DCBHS are theorized to form when massive clouds of pristine hydrogen and helium gas collapse directly into black holes with initial masses of tens of thousands to hundreds of thousands of solar masses. These larger seeds would then have a head start, requiring less time to grow into supermassive black holes. However, the conditions required for DCBH formation, extremely metal-poor gas and intense UV radiation, are thought to be rare. Another possibility is that the accretion rates onto these early black holes were far higher than previously assumed. If these early galaxies were indeed rich in cold gas and undergoing intense star formation, there would have been an abundant supply of fuel for the central black hole. If black holes could accrete matter at or even above the Eddington limit, the maximum rate at which a black hole can accrete without blowing away its surrounding gas with its own radiation, then they could grow exponentially in a very short period. However, sustaining such super Eddington accretion for extended periods also presents theoretical challenges. Furthermore, the observed correlation between SMBH mass and galaxy stellar mass in the local universe might not have held true in the very early universe. Perhaps the co-evolutionary relationship was different, with one component growing more rapidly than the other in the initial stages. JWST's ability to probe the properties of both the host galaxy and its central black hole in the early universe will be crucial for unraveling this complex dance. By studying the spectral signatures of these AGNs, astronomers can measure their black hole masses, accretion rates, and the properties of the surrounding gas, providing invaluable clues to how these cosmic giants first emerged and influenced the evolution of their host galaxies. The story of cosmic evolution, it seems, is not just about stars and galaxies, but also about the mysterious, powerful engines that reside at their very hearts. In the realm of cutting-edge astronomy, especially when pushing the boundaries of what is observable, it's crucial to acknowledge the potential for observational biases. Even with an instrument as sophisticated as James Webb Space Telescope, interpreting faint signals from billions of light years away is fraught with challenges. The very act of observation can sometimes influence our interpretation, and astronomers are acutely aware of these pitfalls as they analyze the data from these early, massive galaxies. One significant concern is the Malmquist bias. This bias suggests that in any flux-limited survey, a survey that can only detect objects brighter than a certain threshold, we are more likely to detect intrinsically brighter objects at greater distances. In the context of early galaxies, this means that JWST might be preferentially detecting the most luminous and massive galaxies, simply because they are bright enough to be seen. If the universe also contained a vast population of smaller, fainter galaxies that are below Webb's detection limits, then our current picture of the early universe might be skewed towards these overachievers. While this doesn't negate the existence of the massive galaxies, it could mean that their relative abundance might be overestimated, or that the average galaxy in the early universe was still quite small. Astronomers are actively working to correct for this bias by developing sophisticated statistical methods and by pushing Webb's observational limits to detect fainter objects. Another potential bias relates to the dust content of these early galaxies. Dust, composed of heavier elements, can absorb and re-emit starlight, particularly in the ultraviolet and visible wavelengths, making galaxies appear redder and fainter. However, in the infrared, dust often glows, potentially making dusty galaxies appear brighter in Webb's MIRI observations. If some of these early galaxies are exceptionally dusty, their observed infrared luminosity might lead us to overestimate their stellar mass or star formation rate. Disentangling the effects of dust from true stellar mass and star formation is a complex task, requiring careful modeling and multi-wavelength observations. Furthermore, the presence of active galactic nuclei, AGN, can significantly complicate matters. As we discussed, an AGN is powered by a supermassive black hole actively accreting matter, emitting vast amounts of radiation. If a galaxy hosts a particularly luminous AGN, its light can dominate the overall emission from the galaxy, making it appear brighter and potentially leading to an overestimation of its stellar mass. While astronomers have techniques to identify and account for AGN emission, it's a constant challenge to accurately separate the light from the central black hole from the light emitted by the stars in the host galaxy, especially for such distant and faint objects. The more powerful the AGN, the more difficult this disentanglement becomes. These potential biases are not reasons to dismiss JWST's findings, but rather crucial considerations that highlight the rigor and caution inherent in scientific discovery. Astronomers are not simply accepting the raw data at face value. They are meticulously analyzing every aspect, developing new calibration techniques, and running extensive simulations to understand and mitigate these biases. The goal is to arrive at the most accurate and unbiased picture of the early universe possible. The very fact that these challenges are being openly discussed and addressed by the scientific community underscores the revolutionary nature of Webb's data and the commitment to truly understanding what these impossible galaxies are telling us about the cosmos. It's a testament to the scientific method, constantly questioning, refining, and pushing the boundaries of knowledge, even when the answers challenge our most cherished theories. It's important to remember that science, particularly cosmology, is a constantly evolving field. Our understanding of the universe is not static. It's a dynamic tapestry woven from observation, theory, and the willingness to challenge established paradigms. The history of astronomy is replete with instances where groundbreaking discoveries forced us to fundamentally rethink our place in the cosmos and the very nature of reality. The impossible galaxies observed by JWST are not the first such challenge, and they certainly won't be the last. Think back to the early 20th century, when Edwin Hubble's observations of distant galaxies revealed that the universe was not static but expanding. This was a radical departure from the prevailing scientific view and led to the development of the Big Bang Theory, a concept that was initially met with skepticism. Yet, the evidence was undeniable, and our understanding of cosmic origins was forever transformed. Similarly, the discovery of the cosmic microwave background, CMB radiation, in the mid-1960s provided compelling evidence for the Big Bang, solidifying its place as the leading cosmological model. Each of these discoveries, initially surprising, ultimately deepened our understanding. More recently, the accelerating expansion of the universe, discovered in the late 1990s, was another profound shock. It implied the existence of a mysterious force dubbed dark energy, which now constitutes the largest component of our universe. This was an entirely unexpected finding that forced a major revision of the lambda CDM model itself, adding the lambda component to account for this cosmic acceleration. These were not minor tweaks. They were paradigm shifts that required scientists to embrace new, often counterintuitive ideas. The impossible galaxies from JWST fit squarely into this tradition of scientific revolution. They are a new set of data points that don't quite fit the existing framework, and rather than dismissing them, the scientific community is engaging in the arduous but exhilarating process of reconciliation. This involves scrutinizing the data for potential biases, refining theoretical models, and even exploring entirely new physical mechanisms. It's a testament to the self-correcting nature of science, where observations are paramount and theories must adapt to fit the universe, not the other way around. This willingness to question and adapt is what makes science such a powerful tool for understanding the universe. It's not about having all the answers. It's about asking the right questions and being open to whatever answers the universe provides, no matter how surprising or challenging they may be. These early galaxies are not breaking the laws of physics. They are revealing the limits of our current understanding of those laws, pushing us to discover a deeper, more complete picture of cosmic reality. They are a cosmic invitation to expand our minds, to embrace the unknown, and to continue our relentless pursuit of knowledge. To truly grasp the profound implications of these discoveries, sometimes it helps to step back from the raw data and consider them through the lens of analogy. Imagine the universe's history as a grand, epic novel. According to our previous understanding, the early chapters, the first few 100 million years after the Big Bang, should have been a slow, quiet prologue. We expect to see only the initial sketches of characters and settings, perhaps a few rudimentary sentences forming. But what JWST has shown us is that these early chapters are already filled with intricate plots, fully developed characters, and complex narratives, much like finding a complete, multi-volume saga where you expected only a short story outline. Consider another analogy: the growth of a human being. We expect a baby to go through distinct developmental stages, crawling, then walking, then running, over many years. Our cosmological models predicted a similar, gradual development for galaxies. Small, simple structures first, slowly evolving into larger, more complex ones. But these early galaxies are like finding a newborn infant already capable of Olympic-level gymnastics. They've seemingly skipped entire developmental stages, reaching a level of maturity that should have been impossible given their age. This forces us to ask, was there a hidden accelerator? A secret growth hormone in the early universe that allowed these cosmic infants to mature at an astonishing rate? Or think of it like building a magnificent cathedral. Our standard models suggested that the early universe was still quarrying the stone, laying the foundations, and slowly, painstakingly erecting the walls. We expected to see only the initial groundwork, perhaps a few half-finished arches. But JWST has revealed that, in certain regions, entire cathedrals were already standing, complete with intricate stained glass windows and soaring spires, at a time when the first stones should have barely been laid. This implies a workforce far more efficient, or a construction method far more advanced, than anything we had conceived. Perhaps the cosmic builders had access to resources or techniques we hadn't accounted for, allowing them to accelerate the entire construction process. These analogies help us visualize the sheer scale of the cosmic surprise. It's not just a minor adjustment to a scientific theory. It's a fundamental recalibration of our cosmic clock and a re-evaluation of the universe's developmental timeline. The universe, it seems, is far more dynamic, far more capable of rapid change and accelerated evolution than our previous, more conservative models allowed. These analogies are not meant to oversimplify the science, but rather to highlight the profound sense of wonder and bewilderment that these discoveries evoke among astrophysicists. They are a powerful reminder that the universe is under no obligation to conform to our expectations, and that its deepest secrets are often revealed in the most unexpected ways. And for us, the cosmic explorers, this only makes the journey more thrilling, more compelling, and infinitely more rewarding. The James Webb Space Telescope has opened an unprecedented window into the early universe, but it is just the beginning of our journey. The mysteries unveiled by these impossible galaxies are so profound that they demand continued investigation, pushing the boundaries of technology and inspiring the next generation of cosmic explorers. While Webb continues its groundbreaking work, plans are already underway for even more powerful instruments that promise to further revolutionize our understanding of the cosmos. One such ambitious project is the Nancy Grace Roman Space Telescope, formerly known as WFIRST. Roman, set to launch later this decade, will have a field of view 100 times larger than Hubble's, allowing it to survey vast swathes of the sky much more efficiently. While it operates primarily in the infrared, its wide-field capabilities will be instrumental in identifying even more of these early galaxies, providing a statistically robust sample that will be crucial for understanding their distribution and evolution across the entire early universe. Roman will act as a cosmic cartographer, mapping out the landscape of the early cosmos and identifying prime targets for Webb's more detailed spectroscopic follow-up. Looking even further into the future, concepts for next-generation observatories are already being developed. Imagine a large ultraviolet optical infrared surveyor, LUVOIR, or an Origins Space Telescope. Missions that would combine Webb's infrared prowess with even larger mirrors and broader wavelength coverage. LUVOIR, for instance, envisions a mirror up to 15 meters in diameter, compared to Webb's 6.5 meters, offering unparalleled sensitivity and angular resolution. Such an observatory could not only detect fainter, even earlier galaxies, but also resolve their internal structures with astonishing detail, allowing us to see the nascent disks, star-forming regions, and even individual star clusters within these cosmic infants. On the ground, the construction of extremely large telescopes, ELTs, such as the European Extremely Large Telescope, EELT, in Chile, the 30-meter telescope, TMT, in Hawaii, and the Giant Magellan Telescope, GMT, will complement space-based observations. These colossal ground-based observatories, with mirrors ranging from 25 to 39 meters in diameter, will be equipped with adaptive optic systems to correct for atmospheric distortion, allowing them to achieve unprecedented clarity. While they cannot observe in the infrared as effectively as Webb due to atmospheric absorption, they will be crucial for obtaining high-resolution spectroscopy of brighter, lower redshift galaxies and for studying the intergalactic medium through which the light from these early galaxies travels. These future observatories will work in concert, each providing a unique piece of the cosmic puzzle. Webb will continue to push the boundaries of redshift, discovering the very first galaxies and stars. Roman will provide the wide field context, revealing the statistical abundance and distribution of these early structures. And the ELTs, along with future space telescopes, will offer the detailed spectroscopic and morphological insights needed to truly understand the physical processes at play. This multi-pronged approach is essential, as no single telescope can answer all the questions posed by these revolutionary discoveries. The ultimate goal is to move beyond simply identifying these impossible galaxies to truly understanding their formation, evolution, and their impact on the universe's grand narrative. We want to know not just that they exist, but how they came to be, what they were made of, and what their existence implies for the fundamental laws of physics and cosmology. These future missions will allow us to probe the chemical composition of these galaxies with even greater precision, to search for the signatures of exotic star formation, and to map the distribution of dark matter with unprecedented accuracy. The journey into the cosmic dawn is far from over. In fact, with these new tools on the horizon, it's only just beginning, promising an era of even more astonishing discoveries that will continue to reshape our understanding of our cosmic origins. Beyond the scientific equations and observational data, the discovery of these impossible galaxies by JWST carries profound philosophical implications. It forces us to confront not just the limits of our scientific models, but the very boundaries of human perception and our inherent biases when trying to comprehend the universe. For centuries, humanity has sought to understand its place in the cosmos, often constructing narratives that place us at the center, or at least within a predictable, comprehensible framework. These new findings shatter that comfortable predictability, reminding us of the universe's boundless capacity for surprise and its indifference to our preconceived notions. One of the most striking philosophical takeaways is the reinforcement of scientific humility. For decades, the Lambda CDM model has been extraordinarily successful, leading many to believe that we were converging on a nearly complete understanding of cosmic evolution. While the model remains robust in many aspects, these early galaxy discoveries serve as a powerful reminder that our knowledge is always provisional, always subject to revision in the face of new, compelling evidence. It's a humbling experience for the scientific community, a call to remain open-minded and to constantly question even our most cherished theories. The universe doesn't care about our elegance or simplicity. It simply is, and our task is to listen to what it tells us, however unexpected that message may be. These discoveries also challenge our perception of time and scale. We, as humans, operate on timescales of decades and centuries. Even geological time, spanning millions of years, is difficult to fully grasp. But cosmic time, with its billions of years, is almost unfathomable. The idea that galaxies could form so rapidly, reaching maturity in a mere few 100 million years, compresses our sense of cosmic development. It suggests that the early universe was not a slow, languid process, but a period of intense, almost frenetic activity. This accelerated timeline forces us to recalibrate our mental models of cosmic evolution, making us realize that the universe's infancy was far more dynamic and eventful than previously imagined. Furthermore, the sheer beauty and complexity of these early structures, observed so far back in time, evoke a sense of awe that transcends mere scientific curiosity. They are luminous beacons from a distant past, whispering tales of creation and evolution that are both familiar and alien. They remind us that the universe is not just a collection of physical laws and particles, but a canvas of unimaginable grandeur, constantly unfolding in ways that defy our expectations. This aesthetic and emotional impact is a crucial, often unstated aspect of scientific discovery, connecting us to the cosmos on a deeper, more personal level. The existence of these impossible galaxies also sparks questions about the uniqueness of our own cosmic history. If galaxy formation was so efficient and widespread in the early universe, does that imply that conditions for life could have arisen much earlier than previously thought? While life requires specific conditions and the presence of heavier elements, the rapid chemical enrichment observed in some of these early galaxies suggests that the building blocks for complex chemistry might have been available surprisingly early. This opens up tantalizing possibilities for the existence of early extraterrestrial life, pushing the timeline for abiogenesis further back into cosmic history. In essence, JWST's findings are not just about galaxies. They are about us. They are about our capacity to observe, to theorize, to be surprised, and to continually expand our understanding of the universe we inhabit. They are a powerful testament to the human spirit of inquiry, a reminder that the greatest discoveries often lie just beyond the edge of our current knowledge, waiting to be unveiled by instruments like Webb and the minds brave enough to interpret their revolutionary messages. The universe, in its infinite wisdom, continues to teach us humility, wonder, and the enduring power of scientific exploration. The very act of observing these early galaxies is a triumph of human ingenuity, pushing the boundaries of engineering and scientific methodology. It's easy to discuss these discoveries in abstract terms, but it's crucial to appreciate the immense technical challenges involved in capturing light that has traveled for over 13 billion years. The James Webb Space Telescope is not just a scientific instrument, it is a technological marvel, a testament to what humanity can achieve when driven by an insatiable curiosity about our origins. Imagine trying to detect the faint glow of a firefly on the other side of the planet, through miles of atmospheric haze and light pollution. Now, multiply that challenge by an astronomical factor, and you begin to approach the difficulty of observing the early universe. The light from these distant galaxies is not only incredibly faint due to the inverse square law, its intensity decreasing with the square of the distance, but it has also been severely redshifted and stretched by the expansion of the universe. This means that the ultraviolet and visible light emitted by young, hot stars in these early galaxies arrives at Webb as faint infrared radiation. This is precisely why Webb was designed to operate in the infrared. Unlike the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, Webb's mirrors and instruments are optimized for infrared wavelengths. To achieve this, the entire observatory must be kept incredibly cold, around minus 233 degrees Celsius, minus 300, now 88 degrees Fahrenheit, for its primary instruments, to prevent its own heat from interfering with the faint infrared signals it's trying to detect. This is accomplished through a massive tennis court-sized sun shield that constantly protects the telescope from the heat of the sun, Earth, and Moon, and passive cooling systems. Furthermore, Webb operates at the second Lagrange point, L2, nearly 1.5 million kilometers, 1 million miles from Earth. This distant orbit provides a stable thermal environment and an unobstructed view of the cosmos, free from the thermal and light pollution of our home planet. But it also means that, unlike Hubble, Webb is not serviceable. Every component, every mechanism, every tiny detail had to work perfectly from the moment of deployment. A feat of engineering precision that is truly astonishing. The deployment sequence itself was a nail-biting ballet of unfolding mirrors and sun shields, a complex choreography executed flawlessly millions of miles away. The primary mirror, composed of 18 hexagonal, gold-coated beryllium segments, had to unfold and align with nanometer precision. Each segment is individually adjustable, allowing astronomers to fine-tune the mirror's shape to achieve unparalleled image quality. This active optics system is crucial for correcting any imperfections and ensuring that the telescope can focus the faint light from the most distant corners of the universe. Then there's the sheer volume of data. Webb is collecting petabytes of information, a torrent of cosmic light that requires sophisticated algorithms and supercomputing power to process and analyze. Astronomers are not just looking at pretty pictures, they are extracting intricate spectral information, measuring the brightness of galaxies across dozens of filters, and modeling the physical processes that give rise to these observations. This involves complex radiative transfer codes, cosmological simulations, and statistical analyses that push the boundaries of computational astrophysics. The success of JWST in revealing these impossible galaxies is therefore not just a scientific breakthrough, it's a testament to decades of planning, engineering, and international collaboration. It's a reminder that our quest to understand the universe is a collective human endeavor, driven by curiosity, perseverance, and the relentless pursuit of knowledge. And with every photon collected, every spectrum analyzed, Webb is not just showing us the universe, it's showing us what we, as a species, are capable of achieving. As we draw our journey to a close, we are left with a profound sense of wonder and a universe that is far more mysterious and dynamic than we ever imagined. The James Webb Space Telescope has not just opened a new window into the cosmos, it has shattered our old one, revealing a landscape teeming with impossible galaxies that challenge our most fundamental theories of cosmic evolution. These hundreds of massive, mature galaxies observed in the universe's infancy are not just anomalies. They are cosmic signposts, pointing us towards a deeper, more complete understanding of our origins. We've seen how these discoveries are forcing us to reevaluate the lambda CDM model, our standard framework for understanding the universe. We've explored the potential explanations, from more efficient star formation and revised dark matter properties to entirely new astrophysical processes. We've delved into the profound implications for the epoch of Ryanization, the growth of supermassive black holes, and even the philosophical underpinnings of our cosmic perspective. And we've marveled at the technological ingenuity that makes these observations possible. But the story is far from over. In fact, it's just beginning. With every new observation, every new spectrum, JWST is providing more clues, more puzzles, and more reasons to be excited about the future of astronomy. The quest to understand these early galaxies will drive research for decades to come, inspiring new theories, new technologies, and a new generation of cosmic explorers. The universe, it seems, is a book with infinite pages, and we have only just begun to read its earliest chapters. So, what does this all mean for us here on our tiny blue dot? It means that we are living in a golden age of discovery, a time when our understanding of the universe is being rewritten before our very eyes. It means that the cosmos is a place of boundless wonder, where the most profound truths are often hidden in the faintest whispers of light from the dawn of time. And it means that the human spirit of inquiry, our relentless desire to know, is our most powerful tool for unraveling the universe's deepest secrets. If you've been as captivated by this journey as I have, if the thought of these cosmic mysteries ignites your curiosity, then I invite you to join us on this ongoing adventure. The universe is a vast and beautiful place, and there are still so many stories to tell. Thank you for joining me on this exploration of the impossible. Until next time, keep looking up and never stop wondering. To fully appreciate the cosmic shockwave sent by these JWST discoveries, we must first build a solid foundation of understanding upon the bedrock of modern cosmology, the lambda cold dark matter model, or lambda CDM. This isn't just a random assortment of Greek letters and scientific jargon. It is the culmination of a century of observation, a grand narrative that elegantly explains a vast array of cosmic phenomena, from the faint afterglow of the Big Bang to the grand tapestry of galaxy clusters we see today. It is, for all intents and purposes, the standard model of cosmology, a framework so successful that it has become the lens through which we interpret almost all cosmic data. The lambda in lambda CDM represents one of the most profound and mysterious components of our universe, dark energy. First inferred from the observation that the expansion of the universe is accelerating, dark energy is a hypothetical form of energy that permeates all of space, exerting a negative, repulsive pressure. Think of it as a cosmic anti-gravity, a force that is pushing galaxies apart at an ever-increasing rate. While we can observe its effects on the large-scale structure of the universe, its fundamental nature remains one of the greatest unsolved mysteries in physics. Is it a cosmological constant, an intrinsic property of space-time itself, as Einstein first proposed? Or is it a dynamic field, a form of quintessence that could change over time? Lambda CDM, in its simplest form, assumes the former, but the truth remains elusive. This dark energy is believed to constitute about 68% of the total energy density of the universe, making it the dominant component of our cosmos. The CDM stands for cold dark matter, another enigmatic but crucial ingredient. Dark because it does not emit or interact with light, making it invisible to our telescopes. Matter because it exerts a gravitational pull, just like the ordinary matter that makes up stars, planets, and ourselves. And cold because its particles are thought to move slowly compared to the speed of light, allowing them to clump together and form the gravitational seeds of cosmic structures. This invisible substance is believed to make up about 27% of the universe's energy density, far outweighing the mere 5% that constitutes all the ordinary, baryonic matter we can see and touch. The evidence for dark matter is overwhelming, even though we have yet to directly detect a dark matter particle. We see its gravitational influence in the rotation curves of galaxies, where stars on the outskirts are moving far too fast to be held in place by visible matter alone. We see it in the gravitational lensing of distant objects, where the light from background galaxies is bent and distorted by the immense gravitational pull of intervening dark matter halos. And we see its imprint on the cosmic microwave background, the fossil light from the Big Bang, which reveals the initial density fluctuations that grew into the large-scale structures we observe today. Together, lambda and cold dark matter, along with the 5% of ordinary matter, form the cosmic recipe of the lambda CDM model. This model provides a powerful framework for simulating the evolution of the universe from its earliest moments to the present day. These simulations, run on some of the world's most powerful supercomputers, can track the gravitational interactions of billions of dark matter particles, the hydrodynamics of gas, and the processes of star formation and feedback. And for the most part, they've been remarkably successful at reproducing the observed properties of the universe, from the distribution of galaxies on large scales to the properties of individual galaxy clusters. But it is precisely this success that makes JWST's discoveries so jarring. The lambda CDM model, with its carefully calibrated parameters and its hierarchical, bottom-up approach to structure formation, makes very specific predictions about the early universe. It predicts a cosmos where the first galaxies are small, faint, and relatively rare. It predicts a gradual, painstaking process of assembly, where massive galaxies like our own Milky Way take billions of years to form. And it is these very predictions that are now being challenged, not by a handful of outliers, but by a growing chorus of impossible galaxies, each one a cosmic rebel, a testament to a universe that is far more complex and surprising than our standard model had led us to believe. The existence of these impossible galaxies, forming stars and enriching their environments with heavy elements far earlier than expected, casts a fascinating new light on one of humanity's most profound questions. Are we alone? And if not, when and where could life have first emerged in the universe? Our understanding of cosmic habitability has long been tied to the gradual chemical evolution of the universe, the slow accumulation of elements heavier than hydrogen and helium, the very building blocks of planets, water, and organic molecules. Traditionally, it was thought that the early universe, being relatively metal poor, would have been largely inhospitable to life. The first stars known as population 3 stars, were massive, short-lived, and composed almost entirely of hydrogen and helium. Their explosive deaths forged the first heavy elements, which were then dispersed into the interstellar medium. Subsequent generations of stars, like our Sun, formed from this enriched material, allowing for the formation of rocky planets and the complex chemistry necessary for life. This process was believed to take billions of years, pushing the timeline for widespread habitability much later in cosmic history. However, the James Webb Space Telescope discoveries challenge this conventional wisdom. If these early, massive galaxies were indeed forming stars at an astonishing rate and undergoing rapid chemical enrichment, it implies that the conditions necessary for planet formation and complex chemistry could have arisen much, much earlier. If these galaxies were already teeming with heavy elements within a few 100 million years of the Big Bang, then the raw materials for rocky planets, and potentially for life, were available far sooner than previously thought. This significantly pushes back the timeline for cosmic habitability. Imagine a galaxy, only 500 million years old, already boasting a rich tapestry of heavy elements. This means that within that galaxy, rocky planets could have begun to form around its stars. If these planets were located in the habitable zone, the region around a star where temperatures allow for liquid water to exist on a planet's surface, then the conditions for abiogenesis, the origin of life, might have been met billions of years before Earth even formed. This opens up the tantalizing possibility of ancient alien civilizations that could have risen and fallen long before our solar system came into existence being. Furthermore, the intense star formation and potentially active galactic nuclei in these early galaxies would have created dynamic and energetic environments. While extreme, such environments might also have fostered unique pathways for chemical evolution, perhaps accelerating the formation of complex organic molecules. The sheer abundance of these early galaxies also increases the number of potential sites where life could have emerged. It's a numbers game. More galaxies, forming more stars, with more heavy elements, means more opportunities for life to take hold. Of course, the existence of heavy elements and rocky planets does not automatically guarantee life. Many other factors are crucial, such as the presence of liquid water, a stable atmosphere, protection from harmful radiation, and a long-lived, stable star. The early universe was also a more violent place, with frequent supernova explosions and intense radiation fields. However, the James Webb Space Telescope findings suggest that the fundamental cosmic ingredients and the necessary timescales for their assembly might have been present much earlier than we ever dared to hope. This new perspective encourages us to broaden our search for extraterrestrial life, not just to mature galaxies in the local universe, but also to consider the possibility of ancient biosignatures or technosignatures from these early, precocious galaxies. It's a profound shift in our cosmic outlook, suggesting that the universe might have been fertile ground for life almost from its very beginning. The impossible galaxies are not just rewriting the story of cosmic structure, they might also be rewriting the story of life itself, pushing us to imagine a universe where life's origins are as ancient and widespread as the galaxies that first lit up the cosmic dawn. Behind every groundbreaking discovery in astronomy lies the tireless work of dedicated scientists and the collaborative spirit of international research teams. The revelations from the James Webb Space Telescope regarding these impossible galaxies are no exception. These findings are the result of meticulous observation campaigns, sophisticated data analysis, and the synthesis of knowledge from countless individuals and institutions worldwide. While many teams are contributing to this rapidly evolving field, a few key studies have been particularly instrumental in shaping our current understanding. One of the foundational studies that highlighted the unexpected abundance of massive galaxies in the early universe came from the CEERS, Cosmic Evolution Early Release Science Survey. This program, one of JWST's first major undertakings, targeted a well-studied patch of sky, allowing for direct comparison with previous Hubble observations. Researchers analyzing CEERS data, such as a team led by Stephen Finkelstein from the University of Texas at Austin, identified numerous bright, massive galaxy candidates at very high redshifts. Their work, published in journals like the Astrophysical Journal Letters, demonstrated that these galaxies were far more common and mature than predicted by pre-JWST models, setting the stage for the broader re-evaluation of galaxy formation. Another pivotal study, directly related to the 300 galaxies mentioned in our title, is the work by Haojing Yan and Bangjung Tom Sun from the University of Missouri. Their research, published in the Astrophysical Journal, meticulously identified these hundreds of candidate galaxies using Webb's NIRCam and MIRI instruments. Their approach, leveraging the dropout technique and spectral energy distribution fitting, provided a statistically significant sample that underscored the widespread nature of these early behemoths. Their findings were crucial in moving the discussion from isolated anomalies to a systemic challenge to cosmological models. They didn't just find a few, they found a multitude, painting a picture of a bustling early universe. Furthermore, the GLASS Grism Lens EIS Amplified Survey from Space Collaboration, another early release science program, used gravitational lensing, where the gravity of foreground galaxy clusters magnifies the light from background objects to peer even deeper into the early universe. Teams like those led by Tommaso Trio from UCLA and others have used GLASS data to find some of the most distant and intrinsically faint galaxies, pushing the boundaries of what Webb can detect. These lensed galaxies, though individually rare, provide crucial insights into the properties of typical galaxies in the universe's infancy, confirming that even less massive galaxies were forming stars at surprisingly high rates. The JWST Advanced Deep Extragalactic Survey program is another monumental effort designed to push Webb to its absolute limits, probing the faintest and most distant galaxies across multiple deep fields. By combining ultra-deep imaging with extensive spectroscopic follow-up, JADES aims to build the definitive census of galaxies in the first billion years of cosmic history. Initial results from JADES have already confirmed some of the highest redshift galaxies ever observed, some existing just 300 million years after the Big Bang, and further solidified the picture of an early universe rich in rapidly forming stellar systems. These research efforts are not isolated. They involve hundreds of scientists from institutions across the globe, sharing data, comparing notes and rigorously scrutinizing each other's findings. The peer review process, the backbone of scientific integrity, ensures that these extraordinary claims are met with equally extraordinary evidence. Every photometric redshift needs spectroscopic confirmation. Every model prediction is tested against the latest observations, and every new piece of data is integrated into our evolving cosmic narrative. It is this collaborative, iterative process that allows us to build confidence in these revolutionary discoveries and to continually refine our understanding of the universe. The names of these surveys and the scientists behind them are etched into the annals of cosmic exploration, marking a new era of discovery ushered in by the unparalleled capabilities of the James Webb Space Telescope. Their work is not just about finding distant lights, it's about illuminating the very origins of everything we see around us. In conclusion, the universe, as revealed by the James Webb Space Telescope, is a far more astonishing and dynamic place than we ever dared to imagine. The discovery of hundreds of massive mature galaxies existing in the cosmic dawn, a mere few 100 million years after the Big Bang, has fundamentally challenged our most cherished cosmological models. These impossible galaxies are not just statistical anomalies. They are profound cosmic puzzles, each one a testament to the universe's capacity for surprise and its indifference to our preconceived notions. We have journeyed through the intricacies of the Lambda CDM model, understanding why these early galactic behemoths present such a significant tension with its predictions. We've explored the potential explanations, from super-efficient star formation and accelerated dark matter clumping to the tantalizing possibility of new physics. We've delved into the critical role these galaxies might have played in Ryanizing the universe, lighting up the cosmic dark ages and their mysterious co-evolution with supermassive black holes. We've also acknowledged the inherent challenges and biases in observing such distant and faint objects, highlighting the meticulous work of astronomers to ensure the veracity of these groundbreaking findings. And we've placed these discoveries within the broader historical context of scientific revolutions, reminding ourselves that our understanding of the cosmos is always provisional, always evolving in the face of new, compelling evidence. Finally, we've touched upon the philosophical implications, how these revelations reshape our perception of time, scale, and the very potential for life in the early universe. The James Webb Space Telescope is more than just an observatory. It is a time machine, a cosmic detective, and a catalyst for a new era of astrophysics. Its golden eye has peered back to the very first moments of galactic assembly, showing us a universe that was bustling with activity when it should have been quiet, mature when it should have been nascent. This is a universe that is richer, more complex, and infinitely more awe-inspiring than we had ever conceived. The journey to fully unravel the mysteries of these impossible galaxies is far from over. It will require continued observations with Webb, the next generation of space and ground-based telescopes like the Nancy Grace Roman Space Telescope and the extremely large telescopes, and the relentless intellectual curiosity of scientists worldwide. Each new piece of data, each refined simulation, each bold new theory will bring us closer to a complete understanding of how the universe orchestrated its grand symphony of creation. For us, the curious inhabitants of this pale blue dot, these discoveries are a profound reminder of the vast unknown that still surrounds us. They are an invitation to continuously question, to explore, and to embrace the wonder of a cosmos that consistently defies our expectations. The universe is a story still being written, and we are privileged to witness its unfolding chapters. Thank you for joining Cosmo Depth on this incredible voyage through space and time. If this exploration into the universe's deepest secrets has sparked your imagination, please consider liking this video and subscribing to our channel for more journeys to the edge of cosmic knowledge. Your support helps us continue to bring these captivating stories of discovery to light. Until our next cosmic adventure, keep your eyes on the stars and never stop exploring the depths of the cosmos. This profound tension between observation and theory is not merely an academic exercise. It represents a potential inflection point in our understanding of the universe. If the Lambda CDM model, for all its elegance and predictive power, cannot adequately account for the existence and abundance of these early, massive galaxies, then we are faced with several compelling and perhaps unsettling possibilities. It could mean that our current understanding of the fundamental constituents of the universe, dark matter and dark energy, is incomplete or even fundamentally flawed. Perhaps dark matter is not entirely cold, or it interacts with itself or with ordinary matter in ways we have yet to discover. Such modifications could alter the gravitational clumping process, allowing structures to form more rapidly in the early universe. The subtle nuances of these interactions, previously thought to be negligible, might turn out to be crucial in the extreme conditions of the cosmic dawn. Alternatively, the crisis might lie in our understanding of gravity itself on cosmological scales. While Einstein's theory of general relativity has passed every test with flying colors on solar system and galactic scales, perhaps its applicability changes when we look back to the very early, highly energetic, and rapidly expanding universe. Theories of modified gravity, though currently speculative, might offer alternative explanations for the accelerated growth of these galaxies without invoking exotic dark matter properties. Such a paradigm shift would be monumental, akin to the transition from Newtonian mechanics to relativity, fundamentally altering our cosmic perspective. Another avenue of exploration involves the very fabric of space-time and the initial conditions of the universe. The inflationary epoch, a hypothesized period of exponential expansion immediately after the Big Bang, is thought to have smoothed out the universe and generated the tiny quantum fluctuations that seeded all cosmic structure. If the parameters governing inflation were slightly different, or if there were additional fields at play, it could have imprinted a different spectrum of primordial density fluctuations, allowing for the earlier formation of massive structures. Probing these earliest moments of the universe, even indirectly through galaxy formation, is a daunting task, but one that these JWST discoveries compel us to undertake. The scientific community is now engaged in a vibrant and intense debate, a testament to the health and dynamism of astrophysics. Researchers are running new simulations, developing novel theoretical frameworks, and meticulously reanalyzing JWST data to find the elusive answers. This isn't a sign of weakness in science, but its greatest strength: the willingness to confront uncomfortable truths, to challenge established dogma, and to continually refine our understanding in the face of new evidence. The impossible galaxies are not just pushing the boundaries of our telescopes, they are pushing the boundaries of our intellect, forcing us to imagine a universe that is perhaps even more wondrous, more complex, and more alien than our wildest scientific dreams. The cosmic dawn, once thought to be a period of slow, gradual emergence, is now revealed as a dynamic, bustling epoch, full of surprises that promise to redefine our cosmic narrative for generations to come. This era, ushered in by the James Webb Space Telescope, is truly a golden age for cosmology. The very questions posed by these impossible galaxies are not roadblocks, but rather signposts pointing towards uncharted territories of scientific inquiry. The challenges they present are not insurmountable. They are invitations to innovate, to rethink, and to push the boundaries of what is known. This is the essence of scientific progress, a continuous cycle of observation, hypothesis, testing, and refinement. And the current cycle, fueled by Webb's revolutionary data, promises to be one of the most exciting in the history of astronomy. The future of cosmology will undoubtedly involve a multifaceted approach. On the observational front, continued deep field surveys with JWST will be crucial, not just to find more of these early galaxies, but to characterize their properties with even greater precision. This includes obtaining more spectroscopic redshifts to confirm their distances and stellar masses, and to probe their chemical compositions in detail. We need to understand if there are systematic differences in their star formation, histories, or elemental abundances compared to galaxies in the later universe. Furthermore, Webb's ability to peer through dust will be vital in uncovering any obscured star formation that might be contributing to their rapid growth. Complementing Webb's observations will be the next generation of ground-based telescopes. While they cannot match Webb's infrared sensitivity for the most distant objects, their immense collecting areas and advanced adaptive optics will allow for high-resolution studies of slightly less distant but still early galaxies. These telescopes will be instrumental in mapping the distribution of gas and dark matter around these nascent structures, providing crucial context for their formation. Environments. The synergy between space-based and ground-based observatories will be key to painting a complete picture. On the theoretical side, cosmologists are already hard at work. New simulations are being developed that incorporate more extreme star formation efficiencies, different dark matter models, or modified gravitational physics. These simulations will attempt to reproduce the observed properties of these early galaxies, and if successful, they will provide concrete predictions that can be tested with future observations. The interplay between theory and observation is a dynamic dance, with each informing and challenging the other, driving us closer to the truth. Beyond the immediate implications for galaxy formation, these discoveries also open up broader questions about the fundamental parameters of the universe. Could the Hubble constant, which measures the universe's expansion rate, be slightly different in the early universe compared to its current value? Are there subtle variations in the cosmic microwave background that hint at a more complex initial state? These are not minor adjustments. They are questions that could reshape our entire cosmological model, leading to a more nuanced and accurate understanding of the universe's birth and evolution. Ultimately, the impossible galaxies are a gift to science. They are a cosmic enigma that forces us to think bigger, to question deeper, and to explore further. They remind us that the universe is not a static textbook, but a living, breathing entity, constantly revealing new layers of complexity and wonder. And as we continue to peel back these layers, we are not just learning about galaxies, we are learning about the very fabric of reality, about the forces that shaped everything we know, and about our own place in this grand, unfolding cosmic drama. The adventure of discovery continues, and with every new photon captured by Webb, the universe whispers another secret, inviting us to listen, to learn, and to be amazed.